Hey everyone, this is lesson 221 from Integrated Math 3 on transforming other parent graphs. So at this point, we have already been introduced to a few functions, um, hopefully even way back. One that I'm actually haven't talked about was a linear function. So that's on, really should be on our list of things to remember. But more recently, we spend a lot more time on these two functions, quadratic function and absolute value function. Here's a reminder of some of those details that you should have already, or you should already be familiar with. So quadratic function, which creates our parabola when we actually graph this out, has its graphing form in the form of y equals a, where a represents the orientation and stretch factor of that function. X minus h, where the h represents a horizontal shift. Is it going to the left? Is it going to the right? Where the positive h value goes to the right, a negative h value goes to the left, but when it is a negative h value, it'll turn this to a plus h. So remember that rule. And then the k at the end will tell us whether it's a vertical, if it has a vertical shift, either up or down. Together, your h and k will tell you your locator point, which for both of these functions, we would call that your vertex. Not called vertex for other functions, but it is called a vertex for these two. All right, but in general, we could just call it our locator point. So same with absolute value. You'll notice the graphing form of both of these are almost identical. The only difference is really what happens around the x minus h. That's the only thing that's changing here. So the a and the k really remain in the same location. X minus h is always still grouped together. I could technically put parentheses here around the x minus h, just so you know there's always going to be parentheses around it. But what happens with that x minus h changes with the function. So quadratic means it's being squared. Absolute value means we have absolute value bars. All right, so these are two functions we've already gone over. I'm going to go over a few more today, and I'm going to go through them kind of quickly. Most of these functions, if we went through them in detail, they would definitely could take a couple hours to do that. So most of the notes or the handout that I'm going to be using today in the video, after this page, I have those notes done for you and ready for you if you would like them. So if you can't figure out how to access them, then let me know so I could get those to you. But for the most part, here's a summary of really everything that we need to kind of get out of this lesson. And that is that there is more than the two parent functions that we've been talking about. So quadratic and absolute value have been the ones we've been talking about. Now there's other type of functions, and we call them parent functions because each function can have transformations that occurs to it. So, which is where the graphing form equation comes in. So when we look at our parent equation assumes that your h and k value are 0 and your a value is 1. So that means it's not really being shifted, it's not being stretched, and by default it's going to have a positive orientation. So that's going to be true for all of our parent equations. So if anytime you see an equation like y equals x squared, you should know that deep down inside, it's coming from this graphing form. It's just that these values have already been plugged in. Same thing with absolute value of x, and then the rest of these. So I'm going to briefly kind of discuss these, and then I'll go into more detail on each one as you're copying this down. So third on this list is our cubic function, which is actually looks very similar to our quadratic. You'll notice that these look almost the same, except the exponent is a 3 instead of a 2. All right, so that's really the only difference. So x squared versus x cubed. And you'll notice the same thing with the graphing form. All right, so everything's pretty much identical except for that exponent is changing. So what we're going to look at is, well, how does that affect the graph? And how does that does it affect our transformations? Same thing with square root. We have been familiar with square root. It's the same way we normally even do like absolute value of a number. Same thing, we've seen a lot of solutions that might look like, oh, that's the absolute value of 7. Or maybe that's plus or minus the absolute value of 3. All right, so we've seen the square root before as an operator, but not necessarily as a function. And so what happens if we actually graph that? What does the graph of that look like? And again, you'll notice the graphing form looks identical to the rest, except around the x minus h, you'll see there's a big square root, which obviously it's the square root function. Exponential is actually one we've seen before. You should technically be already familiar with exponential, but you might not be familiar with how it looks on a graph. And so that's what we're going to look at today, and some transformations of that. So we have looked at exponential growth before, but what does that look like on a graph? And so the default form for this is y equals b to the x. But, I mean, you'll notice this is the only one that actually has a b in it. So we would actually have to determine or choose a specific b value for us to graph it. So all that matters is b is not equal to 0. In the examples I'm going to show you, I believe I'm going to choose b equal to 2. So we're really going to be looking at y equals 2 to the x. You'll notice, again, similar format. This one probably looks the most different than the rest on the graphing form, mainly because that x minus h is in the exponent, right? So just like x is on the exponent on this b, it stays an exponent, except the shift happens with the x as it's an exponent. The plus k still remains at the end. All these k's remain at the end. And just like all the a values, all the stretch factors are being multiplied in front. So notice that similarity between all these functions. And then the last one is reciprocal function, which if you're familiar with this word, like I think at times I might have said, if I ask you, well, what's the reciprocal of 1/3? You might tell me, oh, that's 3 over 1, right? So if you flip it upside down, then that gives you the reciprocal. So same thing if I give you 4 over 5, then reciprocal is going to be 5 over 4. So what's happening here is really we're just taking that x value and we're flipping it upside down, which then becomes 1 over x. All right, so again, in the graphing form, you'll notice this 1 over x. The minus h is still in the denominator, so make note of that. It's not happening after. Don't make the mistake of thinking it's x minus h plus k like this. That would be incorrect. That minus x minus h has to be together. So be careful there when you're writing that out, or maybe even typing it into a calculator. You must make sure those x minus h is completely in the denominator. A lot of times we'll put parentheses around the x minus h just to make sure we know they stick together. All right, so that was kind of like a brief but long introduction and summary of all the functions you need to be familiar with. So in short, if you are super comfortable with quadratic and absolute value, the ones we've done before, and you understand all the shifts up and down, everything that I kind of mentioned above here, if you're super comfortable with this, if there's nothing that stumps you, then my advice to you would be apply all that you know to everything else that we just introduced, and it's going to be the same thing. Stretch factor doesn't change, orientation doesn't change. The h value is still going to shift left and right, and the k value is still going to shift up and down. All right, if you know how to do that and you have these general formulas memorized or written down and near you, then all these should be fairly easy. The main thing you need to know is, what do these graphs look like, which I haven't really gone over yet. All right, so let's start doing that. The following handouts, it's a one-page handout that kind of summarizes each parent function, and I have one of these for each of the 4 new functions. So this is going to be a lot to copy down. So everything that's already here, I'm going to give you a copy of if you have the ability to print that out. If not, you could always just copy it down at a later time or pause it. Everything's already filled out, so I'm not going to be writing down anything, because else this will take 10 times longer. All right, so I'm going to probably take the longest on maybe this first one or so, and then the rest of them I might go through pretty quickly. So this is our first parent function is our cubic. All right, so it's called cubic because we have our x cubed, right? We're graphing x cubed. So parent equation, this is the one that assumes we have no shift, no transformations occurring. This is what our graph looks like. So let me kind of describe it to you in a way that might help you remember this. One is, a lot of times we'll use description as, it looks like it has one arm up and one arm down. So if you're talking about a parabola, if we're talking about a parabola, it's going to look something like this, is U-shaped. Where if I was showing this to you in person, I might hold my arms up like I have 2 arms up. Now, that's why we describe this as having one arm up while one arm is down. So that's one way of thinking this. And it really is kind of like a parabola, except where half of it gets flipped upside down. So it's almost like half of it has a positive orientation and the other half has a negative orientation. Now, it's not quite the same as a parabola because it is being cubed, so that these numbers are actually growing faster. So you might notice it looks a bit thinner than a normal parabola. So I've created this table of points for us to just let you know, when I plug in a -3, it's going to give me a -27. I actually get negative numbers when I plug in a negative. So unlike a quadratic where it's always going to give you positive. So that's why we end up with a graph that keeps going down when we go in the negative direction. But we describe a graph or its orientation based on how it ends. So imagine we're reading left to right. If we're going left to right, when we head in a positive direction, where is the graph going? So we'll notice the graph is going up in a positive direction. And it's actually, not only is it going up, but it actually keeps getting wider. It's actually going to the right. So it's going up and to the right, that's a positive orientation. So on the right side, I have a lot of extra information. You need to know the general format, the graphing form, which I gave you previously. Orientation, you need to be able to tell me what the orientation is of the graph. Domain and range, we haven't talked a lot about domain and range, but I like to bring it back into discussion when we talk about these functions, because we need to know what values can we actually plug in. Is there any x value that we are not allowed to plug in? Is there a limit of which ones we can or cannot? For domain, we could pretty much plug in any x value. So anything from negative infinity to positive infinity. Another way of writing that is to say all real numbers. So all real numbers, you could either write the words all real numbers, or you could actually use this mathematical symbol that looks like a capital R with a little bit of an extra bar on it. So so if you do write this capital R, make sure you include the extra bar on it as well. So with a domain really tells us what x values we could plug in, which indicates really how wide this graph might go. Range will tell us what outputs we might get. So that means for all those x values that we're plugging in, every time we plug in an x, what's going to be our output? So every time we plug, I'll just do this on the table. Every time we plug in an x, what are these y values going to be? So are they all positive or are they all negative? Do they stop at a certain number? For this one, it's again going to be all real numbers. All right. Other things we want to look for are, is there any intercepts? X-intercepts, Y-intercepts, we always want to look for those. So in this parent graph, only this parent graph, this will change depending on transformations that occur. But if I look at this, it crosses the x-axis at 0, 0, and it actually crosses the y-axis at 0, 0. So the 0, 0 happens to be both an x-intercept and a y-intercept. If for some reason I transform this graph, let's say I just move it, right? If I move it over here, then my x-intercept and my y-intercept could possibly change, right? Or let me change it so it's very clear I have different ones. So if my graph was right here, then that would mean I have an x-intercept and a y-intercept that are different. So keep that in mind. Those values will change if your graph has been transformed. Locator point, like you're already familiar with, is your h and k. In this case, where is our locator point? Well, a locator point is going to be right in the middle. So if I move that one point, the rest of the graph moves with it. So that's the nice part about knowing where the locator point is, right? Similar to our vertex. Now we don't call it a vertex on the cubic. I would just call it the locator point. So make sure you know that. So this is your locator point. All right. And asymptotes, we don't have any here. I'll talk about those when we actually have one on one of the other functions. All right. So that's a long explanation of this. Now I'm going to go through all this with all the functions. But before that, the whole point of this lesson is not only so you could be introduced to these parent functions, but to understand their transformations. Now I kind of summarized it, telling you that all those equations kind of look the same. Here's kind of a visual of what that looks like. All right, so I'll summarize this, and this will be done for all the functions, so I won't necessarily talk about it with all of them, but I need you to understand that there's different families, right? So there's transformations of that parent graph. So if we look at just the horizontal shift, right? So if I just want this graph to shift horizontally, left or right, the graph's going to stay the same, right? The graph's going to stay the same. It's just going to go either more left or it's going to go more right. So how much it moves to the left and right is going to be based on the equation. And so that's where our h value comes in. So which parameter causes the graph to appear as it does? Well, it's that negative h value that's going to make it shift to the left. And if it's a positive h value, like if it's a positive 3, then it's going to shift to the right. All right, so that's why this one's shifted to the right. So don't forget the default is going to have an x minus h. So when I say it has a positive h value, that's correct because that's always going to be a minus, right? That's always going to be a minus until you plug in a negative number, like on this one. You plug in a negative 3, then negative 3 becomes positive 3. So just as a reminder on that. All right, so just like a horizontal shift, right below that I have the vertical shift. Same idea. I have the same graph. The only difference is it literally has been shifted up and down. So I could literally take this and show you that I could put it right on top and it's going to be the same graph. The only difference is it's going to be shifted up or down. And you'll notice there is no more h value. What we've done is we've put a k value. So the k value told me it's going to shift up. If it has a +2 and if it has a -2, it's going to shift down. All right. Hopefully you remember all this from our quadratics when we talked about this with our quadratics and absolute value. Same thing with the stretch factor, right? So when we only want a specific stretch, we are looking at the a value, so the value in front of the function. So if that's a big number, if it's a number greater than 1, so if we actually look at that absolute value of that number, so if for some reason it was like a -2, I'm only focused on absolute value of that, which is 2. So if that's a 2, means it's going to look stretched. It's going to look skinnier, right? Cubic was already skinny. Now it's going to even look more skinny. Unlike a fraction, where the graph, it's hard to tell because the original cubic was already skinny. This is actually wider. So hopefully you could compare these two and you could tell that they are not the same. So if I actually put them on top of each other, you should see that one is skinnier than the other. All right. This one would be stretched horizontally, or another word would be compressed. All right, and then the last one is the orientation family. Common question I've been asking you, can you tell if it has a positive orientation or a negative orientation? And so this is really the only time it kind of looks different. So this first one is identical to the parent function. All right, this is y equals x cubed. So that's what we started with. It is positive because of how it ends. So I'm looking at the right side, and I notice that it's going up. When it has a negative orientation, when we have a negative orientation, you'll notice it's going down. All right, so that's what we're focused on. It doesn't really matter what happens before. What matters is how it ends. All right, so when that graph goes down, you know it has a negative orientation. So as soon as you see an equation like this, you should already know. You should see the x cubed and be thinking like, oh, I know that's the one that has one arm up, one arm down. And then you see the negative and you're like, oh, now it's switched the other way. So keep that in mind when you're sketching these. All right. So that's a long explanation, but I needed to spend more time on this one. Again, all these are already written out for you, and I have these available for you for those of you that are in class. If you can't access it, let me know, or email me if you need a copy of this. or if you want a blank copy of this as well. All right, so the next function is our square root function. If you can't get a copy of the notes, I would recommend at the very least that you're copying down this top portion, and I think you should be fine with just that for each one, because you need to know what these graphs look like. And so this one, square root function, obviously has the square root. We've already gone through graphing form. When we plug in numbers, we've talked about this before, when you plug in a number to a square root, it doesn't work nicely with negatives, right? So if we want real numbers, this coordinate plane, x and y axis, only has real numbers on it. So even though we're okay with imaginary numbers, we can't necessarily graph them on a real axis. So when we plug in numbers, like on this example, I plugged in a -4. -4, if you put that in a calculator, it's most likely going to give you some type of error. Depending on the calculator you're using, it might give you a different error message, but it won't give you a number answer. So that means if I try to plug in -4, there is no output. It's not working. If I plug in a 0, it does give me 0. When I plug in 1, it does give me 1. I picked certain numbers that would give me nice numbers. I knew I'm working with the square root, so I chose perfect squares. I want to plug in a 4. I want to plug in a 9. I plugged in 16 and 25, but those don't even fit on the graph. So I only plotted what fit, even though my table has more. Now, a common way of describing this is that it kind of looks like a parabola on its side. So we call this a half of a sleeping parabola. Now, you should be familiar with a parabola that looks like this, right? So it looks like a U-shaped. And so a sleeping parabola looks like this, right? That's what it's called. It's the name, a sleeping parabola, which we haven't gone into that quite yet. But if I only have half of it, then it gives me my square roots. So if I actually put 2 square roots, I put one on top and one on bottom, then it completes my sleeping parabola. All right, so you'll notice, so there's nothing here, but this can be transformed, right? I could very easily move this wherever it needs to be moved, but that graph doesn't change. And so the key point here is going to be this. Here's your locator point again. Kind of looks like where the vertex would go if it was a parabola. All right, so there's your locator point, and positive. It's headed in a positive direction, and you'll notice the domain. I can only plug in x values that are greater than or equal to 0, right? I can no longer plug in negative numbers for this to work. And because I can only plug in positive numbers, I'm only going to get positive outputs. So my range will always be something positive as well. All right, in this case, our x and y intercept are both at the locator point, and there are no asymptotes. All right, so here are all the transformations in case you need to see these. It's the same idea as the previous function. You should notice I literally took this same graph and I shifted it left and I shifted it right and I shifted it up and I shifted it down. All right, so you'll notice it's literally the same graph. I just shifted it. So when we talk about horizontal shift and vertical shift, keep that in mind. It's exactly the same as the original. It's just being shifted. Right? The only time it's going to look different is if it's being stretched. So that's the only time. So you'll notice on this stretch factor, when we have a 2 in front where it's supposed to look skinnier, this is a this is a vertical stretch. So it's being pulled up. So imagine someone grabbed onto the graph and they decided to pull it up. They're pulling it up. That's why it looks taller. Versus if someone grabs it and they decide to pull it to the right, and then it's going to flatten out. All right, so, or sometimes people think of this as someone pushing down on it, which is why we call it compressed. All right, so again, you'll notice the A values are different. Whole number, a big number greater than 1, or a number greater or between 0 and 1. So make note of that. This is the same for all these functions, so sorry if I'm repeating myself, but I need you to know that these are the same. So again, negative orientation, this is one, there's a common mistake. A lot of times when I ask people to graph the negative orientation of the square root, a lot of times people will graph it to the left, right? They think, oh, I'll just go to the negative direction, right? But that doesn't work. We are flipping all the y values. So every y value, right, that's us going up and down, all of a sudden becomes negative. So that's why it's all below. So this negative, don't forget, is outside of the square root. It's not inside. So it's okay if there's one on the outside. That's where it's going to flip it across. It always flips it across the x-axis. All right. And then, all right, we have 2 more. Exponential function. So here we have our y equals b to the x. I mentioned before, I'm going to specifically choose b equal to 2. You could choose any number you want, but the graph will look different. I think the easiest for us right now is to make sure we're all focused on the same one. 2 to the x is probably the easiest for us to work with right now. You can't use really 1 to the x because then that's just going to look like a straight line. So 2 and greater, 2, 3, 4 would probably be the limit for me. All right. So this is the only one so far that actually has an asymptote. So you'll notice the asymptote is actually an equation of a line, and that equation for us, for this one, is y equals to 0. So y equals to 0 is this line right here for right now, which can be moved, but the reason why we call this an asymptote is it's really an imaginary line. It's not actually part of the graph, but it's an invisible line like a force field. And if you could imagine, this is like a roller coaster, this exponential. It kind of looks like it was going to be a parabola, but it's not. It actually keeps going down, like if it's going to hit the ground, but it never actually touches the ground. It'll never hit it. It'll get really close, but never touch it. So because it never touches this line, we call it an asymptote, but it gets really close to it. All right, so you could see as we plug in numbers, if we plug in numbers, I'm going to go right to left. I plug in a 3, I get an 8. I plug in a 2, 4, 1, 2. You'll notice these numbers are cutting in half. So 8, 4, 2, 1. And then as soon as I go to the negative 1, it turns into, again, I'm cutting 1 in half. That's 1 half. And then I cut that in half. That's 1/4. And I cut that in half and I get 1/8. These y values are getting really, really tiny, so tiny that it becomes almost impossible to graph. So you just kind of have to do your best in graphing those. The easier ones would be over here. But if you just graph this and you stopped and you didn't show someone the rest of the graph, they might think this is half of a parabola. So you need to be careful. You need to show them that this graph actually keeps going, and you don't want to make the mistake of drawing one that goes underneath the asymptote, because it's never supposed to cross it. All right. All right, in this case, you'll notice because the asymptote's at y equals to 0, there is no x-intercept, but there is a y-intercept at 0, 1. It does cross it there. So this changes, obviously this changes with our shifting, and we notice it more with the vertical shift. So as you can see, look at all these graphs pretty much look the same. I could literally copy this and move it to on top of all these, as you could see. I just like to show you that to let you know these are all the same graph. So the only difference is whether it's shifted to the left and shifted to the right. And you'll notice again, the x value is an exponent. So when we put our h value, it's also going to be part of the exponent. So it's going to look like a tiny little +3 or -3. Now these are all examples. Obviously you could use any numbers you want. I just try to choose numbers that seem simple. I chose an a value that was similar to ones we've seen before, 2 and 1/2. And probably this one's a little bit harder to tell on the stretch factor. The graph doesn't always look too different, but it will start to round. When it starts to round right here on the bend, it'll start to look a lot different. So I think after you see a few of those, you start to notice the difference. Now the key here, I wanted to focus on was the vertical shift, because this is the one where your k value actually tells you where your asymptote is going to be. So in this case, you'll notice the +3. The +3 is 1, 2, 3. That's exactly where your asymptote is, and that's where your graph cannot cross. Here it's a -3, so it went down 3, and that's exactly where your asymptote is, and it can't cross that. So this is a little bit different, or it's, I guess, additional information for you. When you're looking at these graphs, the k value actually gives you a little bit more information because we have an asymptote here. So keep in mind with the negative orientation again, you'll notice all that happens is it flips upside down on the other side of that asymptote. And you should notice it's still ending in a positive direction when it's positive, and it ends in a negative direction when it's negative. So make sure you pay attention to that. That's the only time it looks flipped upside down. All right, and then the last one for us is the reciprocal function. And this one is a bit different than the others. It resembles a couple of different functions from before. And if you didn't notice, it actually has, I'm going to remove these asymptotes for a second. So it actually has two separate curves. So not only does it have two separate curves, but it actually has two asymptotes. So you'll notice at the bottom here I have x equals to 0 is 1, which means that's this line that goes up and down. And it also has y equals to 0, which is this line that goes across. So these graphs get really close to these asymptotes but never actually touch them. And so they kind of look like this. They're similar to parabolas, except they look like they've been forced to stay in each quadrant. So it's almost like they're stuck in this corner, and then they're stuck in this other corner. So there's a copy of it. So these are mirror images of each other. So it's almost like there's this line of symmetry that goes down the middle, right? Which there is. All right, so we've seen the equation. I've shown you this before. Things to note. How do I know if this is positive or negative orientation? Because this one keeps going down, and this one is going down also, keeps going down. Again, we're always looking to see how it ends, and in this case, when we go further in x, we're always going to have a positive y value. So we call this positive orientation. So I've put these numbers here for a reason, in case you didn't notice. These are our quadrants. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. They go in a counterclockwise direction. And I just wanted to make a note that the first and third quadrant is where the graph is, unless it happens to be a negative orientation, then your graph will be in the other two quadrants, which I'll show you in a second. All right, so the one neat thing about this graph is if you actually put in a 0, if you actually put in the point where these asymptotes intersect, that you should end up with an error message. But everything else is fine. You could plug in any number you want, and you could plug in any x value. It might give you a really small fraction, but it's going to give you an answer. So for domain, the only thing really we need to say is you can plug in any number, except you can't plug in 0, and you can't plug in, you'll never get a 0 for y. All right, but that's only for the parent function. This will change, this information changes as well as the x-intercepts and locator point. Actually, all this stuff changes based on the transformation. So let's look at our different transformations of this. As you can see, they pretty much look all the same. Subtle differences, and I'll zoom in on this one for a second. Horizontal shift, we are looking at, if I take this, I could shift it. I could shift this left and right, up and down. So if I actually move this, you'll notice the exact same graph, except it's been shifted. So keep that in mind. I like to always just show you that, remind you, they're exactly the same. You should notice your h value is on the bottom with your x value. With the vertical shift, this is again the same graph, just to remind you that. And so shifting up and down, right, you'll notice it's the same graph, except I can move it up or down, which then changes the asymptote. So the equations, your equations of your asymptote would change based on where that is. So then we'd have a new intersection of those asymptotes. All right, and then the last one, probably the key one here that I mentioned before, is the negative orientation, noticing that it's shifting. When it's negative, it's on the bottom, right? It's in the negative area, versus when it's positive orientation, it's up on top, right? So that's that. And then, oh, the other thing was the stretch factor. This one we kind of noticed it a little more. So if I put in a stretch factor of 3, you should notice the space between these two increases, right? Unlike like if I show you this one, you'll notice they look very close, but as soon as I stretch them, they're being pulled apart. The stretch is being pulled apart. When I put a small stretch factor, like 1/3, you'll notice these get very close, right? These 2 points get very close. So it almost looks like a right angle, right? This curve looks very tight versus here it's a very wide turn. All right, so things to notice on all these. So if at any point or if you have questions about any of this, if you're copying this down, you need extra time to copy this stuff down, just rewatch the video and then pause it so you can get it down. Hopefully you're able to get the copy of these notes so you can have it as a reference. So I'll go back to this screen just to remind you. Here's all the functions that we talked about. And the ones that you need to know. Make sure you understand their graphing form. If I give you one of these equations, let's say like a square root equation that's perfectly filled out, maybe if I say, oh, here's y equals 3 times x minus 2, square root of x minus 2 plus 4, and I ask you to tell me about this graph, you should be able to tell me where this graph is located and what it looks like, right? You should be able to say, oh, well, it has a locator point at 3, 2, and it's gonna look like this, right? So you should be able to give me a sketch and a general idea of what's happening. Does it have a positive orientation? Does it have a negative orientation? So, all right. Let me know if you have any questions. Hopefully most of this made sense. And that's it for now.